We are still ticking along in the final stages of kind of fundamental mechanics. Hopefully, it's all basically rehashed for you guys, and you're completely across it based on CS 2001. Obviously, I need everyone to be pretty much at the same point. So if you miss some things in CS 2001, hopefully I'm filling that in. I guess the last sort of area that we're going to talk about is stress concentration and then residual stresses. And residual stresses we'll do on Tuesday. Have you guys seen anything to do with stress concentration thus far?
One slide.
One slide, okay, good. Well, I have about 20 slides today, so but it won't take that long, so that's all good. So stress concentration is quite important. It is a geometric kind of impact on the stress. So everything we've done so far is really simple geometries: rectangular cross-section, circular cross-section. We assume shaft is completely even the entire length. Obviously, that is not the case in any machine component almost. Particularly with shafts, you'll have steps for bearings and bushers and gearing and all of that kind of stuff. All sorts of different changes in that shaft. And you need those to be able to retain the shaft and make sure it doesn't, go off axially or make sure bearings don't slide off in the wrong direction or anything like that. So they're very important geometric features, but they have an effect on the stress. Two images very simply. The easiest way to think of stress concentration is the effect that the concentration has on force or the flow of force through the atoms of the material. Okay, so we've been talking about this idea that atoms, basically the atomic bonds get stretched by force. You put too much force on them and the bonds break, but put a certain amount of force on them and they'll stretch, and that stretch, that density of force being carried by an atom is stress. And we can sort of draw lines like this. So if we have a nice straight section with an axial load, the idea is each atom kind of carries that load evenly and passes it on to the next one, and you've got flow lines of that force that are nice, straight, evenly distributed lines, obviously, or ideally. And so the result of that is a stress profile that has a nice, straight face like that, and we've talked about that. Now, if you introduce one of these geometric discontinuities, or a notch, or a crack, or a step in a shaft, or a corner, or really anything that changes that profile, what happens is that those force lines change. The way that you distribute the load throughout the atoms change. So let's forget about what shape this is for starters. If we have a certain area here, an amount of force that the atoms are carrying, and then we decrease that area, forgetting about how we got there. We decrease the area, but the same amount of force needs to be carried. So what's the stress do in that narrower section? Increase, yes. And then if we increase our area again, you'll go back to the previous stress. All right. So in a perfectly ideal world, you are going to have more stress here, and so forgetting about the way that the notch works, we have to calculate stress on that area. Now, if you have enough of a transition from the wider to the narrower and back to the wider again, or just narrower if you've got to step down or whatever, enough of a transition, the atoms over on, let's say, this side, there's enough room for them to fairly evenly transition that force into the atoms to the right, okay? And so this atom on the left has a certain amount of force, and maybe two atoms on the left have to apply that load to one atom on the right, so the one on the right gets more stress because it's kind of joining those two forces together. So if you've got enough of a gradient, then the atoms have a chance to sort of evenly distribute that, and you don't get any stress concentration. The challenge is that takes a very, very gradual gradient to achieve that. What we actually want to do is do things like sharp steps and notches and that kind of stuff. And as soon as you do that, the atoms in the middle of the material, they're sweet. They're nowhere near that notch, so they can just evenly distribute that force the same way they would have with the big long gradient. But near the notch, because these guys up here have to get all of their force, and it bottlenecks, and those force lines bottleneck around that notch. And so you've got much more force trying to go through these atoms here than you do these ones in the middle there, because they've had much more of an opportunity to redistribute that load. And so what that's called is stress concentration, because the concentration, the collecting, the bunching up of that force line around a notch will cause more stress. So higher force density, higher stress. All right? And so what we find is, if you have a notch like this, instead of a nice even distribution like we might like, easy to analyse, what we end up getting is, this is in the centre part, nominal stress. So that's just the stress that you calculate force on the area in the reduced area. So it's more than the left and right, but it's just that nice even stress. But at the top and bottom we get a peak. And that peak is that stress concentration. And it looks something like this. So you get the maximum right at the edge of that notch. And then it'll kind of decrease down to where the nominal is and increase back up at the bottom of the notch. Okay? So stress concentration will cause a large maximum, which is important because if you were to choose a stress element to draw your applied stresses for, firstly, you'd know that you want a stress element at the top there, and that it's an axial load, but through that cross section you don't have even distribution, so it's going to be different between the middle and the top and the bottom. So that tells you want one at either the top or the bottom. Secondly, if you just calculate P on A like we ordinarily do, you've not got the correct stress for that stress element. You need to do something else. You need to account for that extra stress that's coming from the stress concentration. And the way that we do that is a very simplistic way, at least the way we do it calculating by hand, is a very simplistic way. We use a factor called a stress concentration factor. And so you'll calculate your sigma value, sigma max, based on KT, which is a stress concentration factor, multiplied by the normal stress. And that's just the stress if you had a perfect gradient, you didn't worry about stress concentration at all. So it's still calculated on the reduced area, but you know, that's just that easy P on A calculation. So for this example, here, let's say that's a rectangular bar. Area is the reduced area. Nominal is P on A for that reduced area, but that's not our maximum stress. That's our stress probably in the middle here. But our actual maximum stress we would have to multiply by some sort of a factor. We need to calculate what that factor is, or determine what that factor is. Now, note that I've got a KT and a KTS because normal stress and shear stress, those factors might be different. Remembering that our distribution of stress looks different for different modes of stress. So for bending stress, you've got sort of that gradient like that, and for transverse shear, you've got the circular arc, and for normal stress, you've got a straight line. So the amount of sort of congregation of force lines for each of those different modes of stress will be different. And so we need a different factor for each of those modes of stress as well. And so I'll talk about that. Alright, so you've got a bunch of tables in your textbook, and what I wanted to do with these couple of slides is to kind of show you how those tables have been calculated. Just as a bit of background, you're not going to need to do this. You can do this. I think one of the workshops in EG 3001, at least when I ran it, was to actually calculate stress concentration factors. But this is kind of to show you how those tables have been calculated and what they mean. And so what I did, this is just a really simple example. We've got, let's say, a plate. It might be a certain dimension, or it could be infinite in the horizontal direction. It doesn't really matter. It's got some load P, and we have some sort of circular hole in the centre of that plate. And this circular hole, if you say that the width of half of it is A, and the width of the height of half of it is C, if we vary that ratio of A and C, we're going to get a different characteristic notch or different characteristic hole. So, for example, if A is large and C is very, very, very small, what does that look like? So if A is large and C is very small, what do we got? Basically a sliver, a slice, a crack. And if A is very small and C is large, what have we got? A vertical slot. and some ratio between the two. You go from a vertical slot, it can merge, and if you change that ratio, you'll get to a horizontal slot. And because finite elements are really useful, and finite elements will actually calculate the stress concentration for us, because that's exactly what they're doing. You've got all these elements, and one of these elements, if one of these elements goes to two other elements, it's got a certain amount of force, and it needs to distribute that force to the other two elements, exactly the same as the atomic analogy that I used. So that's how FEA works. And when you do FEA, you don't need to use a stress concentration factor because it's actually calculating it by default. It's got the elements, it's doing that naturally, which is why it's so powerful. So what I did was, I did all of these different combinations of C and A for all sorts of different combinations in that slot, and then you can calculate what the critical stress is. And this is just half that plate, so this is just the top right-hand quadrant. And you can see that this red zone on our contour plot, that's where the maximum stress is occurring. Yeah? And so this is a zoom in on that, showing a mesh, and I've got a nice fine mesh, so I'm making sure I got it accurate. And for that example, this one's the circular hole, so that's where, let's say, C and A are 0.01 metres each. So that's a perfect circle initially. And I'm calculating the maximum stress at this point as, what is that, 3.36 megapascals. And if I just used this amount and didn't have a notch and I just went straight up and applied the same force to it, that would be my nominal. That would be my nominal stress that I was talking about. And I've calculated that just by putting a point out here because that's unaffected by the notch. And my nominal stress is 0.8 megapascals. So what I can get is a ratio between my nominal stress and my maximum stress. If I go back here, look at this equation. If I took my nominal stress over to this side of the equation, sig max divided by nominal stress, I get my KT. Yeah? That's exactly what I did. So from 0.01 to 0.01, I've got a KT factor of about 4. Alright? So let's think about this. That's a circle, and that circular hole is causing a stress concentration of about 4. So your stress at the tip of that hole is 4 times what it would have been if it was just a perfectly rectangular cross section. It's quite a lot of stress. And so that's quite important in your calculation. Now let's look at some of the different options. Remember we said if A is big and C is small, we've got a horizontal slot. So if A is big, let's say A is 0.1 and C is small, where's my small c? There. So if A is 0.01 and C is 0.0001, what's my stress concentration factor? Pretty high, 58. So we've got what is almost a crack, and the stress at the tip of that crack is almost 60 times the nominal. Alright? So you see that a crack is really, really critical for stress. Alright? What about the opposite? If we've got a vertical slot like this, A is very small, C is very large. An example of that, C and A. What's my stress concentration factor? Yeah, 1. It's almost negligible, the difference. And if we think about it, for an axial load, if I've got a vertical slot, does that vertical slot have any effect on those force flow lines that I was talking about? Do they need to bunch together at all? No, absolutely nothing. Alright? And when you're talking about axial loading, there's no horizontal transmission of force. All of the force is up and down. Now, it's not necessarily the case for other things like bending and that kind of stuff, shear, certainly. But a vertical slot has almost no effect, and if it's infinitesimally small, if it's literally just 2 pieces of material touching in the centre there, it shouldn't have any effect, and your stress concentration will be 1. Okay? And so that's an example just for a slot and a hole. And if I was to take these KT values and plot them against some sort of geometric property, now I can plot them against C and A. What I'm actually going to do is plot them against the ratio of C on A, because that gives me sort of a more general kind of an approach to it. The only geometry that I know about this is C and A, and the ratio between the two will tell me a lot. So when C on A is big, that means I have a vertical kind of a slot, and this should be small. And when C on A is small, that means I have a horizontal kind of a crack, and then that's going to be big. And so I plot them. C on A on the horizontal, and I go KT up here, then you can see I have a nice kind of exponential looking line, such that if I wanted to analyse this, and I had a plate with a hole in it, and I knew what C and A were, I calculate the ratio of C on A, and I can find what my stress concentration is straight from this plot. Right? And now I don't need to do the Anderson test, I can just use the plot and I can do it by hand. Alright? And that's called a stress concentration plot or stress concentration factor curve. Alright? And in your textbook, and the reason that I asked you to bring your textbooks today is because there's pages and pages and pages of them. Alright? So for all of these different types of geometry that we might want to analyse by hand, your textbook has pages of these stress concentration plots. Now this is page 163 in your textbook, that's the first one. And you can see that these ones are for a shaft with a step in it, and that step has some sort of a radius. And the geometric properties here, we've got D being, capital D is the big diameter, little d is the small diameter, radius is R is the radius of the notch. And you'll see that there's three different diagrams. This one is your factors for bending stress. You can see because we've got the moment on the end. This one's your factors for axial, and this one's your factors for torsional. Right? So you have different factors for the different loading mechanisms or modes of loading. If you were to do a stress element at some critical point that has a notch, and you calculate all your applied stresses, then you might apply different KT values for those applied stresses for each of them. So if you have a shear stress from torsion, you choose a KT from that. If you have a KTS from that. If you have a normal stress from bending, you choose, so the KT and KTS value goes to each of your applied stresses before you then calculate a principal stress. Okay, and that way you can accommodate all of the different types of modes. So that's for our circular shafts. This is for a circular shaft with a notch, so D goes down and D goes up. Similar sort of deal, a few different loading scenarios. This is for a circular shaft with a radial hole through it. So obviously, if you've got torsion or whatever, a hole through the centre of the shaft will be detrimental. There will be stress concentration there. You might have like a grub screw or something like that you want to hold some piece of machinery on with or a pin going through that. Once again, you've got all three modes here, and in this case, this line's the axial one, this one's the bending one, and this one's the torsion one. When you're in, you get the maximum stress on that hole in terms of throughout the cross section.
Right.
Yeah, probably just on the edge up there. Yeah. So either on the base face or on the side of it, depending on And for just to be critical, you just choose one of them and then just use the worst case scenario, the bend and torsion and everything at that point. But that point's the point where that stress concentration is going to come to bear on the maximum stresses. Okay, so you just choose a point somewhere on that edge, on the edge of the actual hole, and that would be the point to analyse. Alright, these guys are plates. Plates with a step, with a bending, plates with an axial load. These ones plates with a notch, so height goes down, height goes up. This one, plate with a hole in it, and this has a bending, so the plate's like this and that has a bending on it. This one is a plate where the hole is being loaded, so that's like a pin or a bolt or something actually applying the load to the hole. This one, we've got a hole, but you're applying the load to either end of the plate. Okay, and so this one is this line, this one is this line. That might be, and then this guy is some sort of a T-junction where you might have load being applied to the centre there, and it's carrying some sort of a bearing load on either side. So there's lots of different options. If you have a geometry that isn't taken care of in these plots, you'll probably be able to find equivalent plots online for different common geometries. If you have a geometry that's not common at all, maybe you need to actually use some finite elements or something like that for more complicated geometry calculations. Okay, now let's have a quick look at, I've got a couple of examples here to have a crack at these. What are we going to do? Let's do this one first. So, let's have a look at how these work. Remember, it's exactly the same as my finite element one that I was talking about. So you've got some geometric quantities, and then the plot uses ratios, so it non-dimensionalises it by using ratios. Otherwise, you'd have to have a different plot for every different size shaft, which would be a real pain. And so the first non-dimensional ratio in this case is little r divided by little d. So that's the radius of the notch divided by the diameter of the smaller part of the shaft. So the first thing you do, if you've got a shaft like this, you go ahead and what's my radius, what's my diameter, what's the ratio? Alright, this is where I am on the horizontal. Next thing you do, big D on little d. So what is the ratio between the two different diameters of my shaft? Calculate that ratio, work out which line you are. By the time you have a line and you have a horizontal, then you can get to a point, and over on the left there you read KT. And KT is what you apply to your normal stress. Now, which diameter do I use to calculate my nominal stress? Big D or little d? Little d. Yeah, little d. So, smaller diameter or smaller area, same force, more stress. Yeah. So you always use basically the area right at the tip there. So right where that radius, the narrowest point is closest to the radius, that is the exact point where that stress concentration will occur. So the narrowest point, but still close to that radius. Okay, so what I want you to do is find me a KT value. Alright, I have a circular shaft. I have some axial loading, that's important, that tells you which graph I need to use. P. Alright, I have a 20 millimeter diameter, I have a 40 millimeter diameter, and I have R5 millimeters. Find KT. Hopefully if you've got your table in front of you, it'll be easier than looking up on the board, but either way. Now obviously there's going to be a bit of read error when you try to use these plots. Try and use rulers if you can, because it will mean that you get nice straight, at least approximations. And it's a good rule to read the value twice. Alright, so read it once, write that down, come back and look at it and read it again, because it's really easy to confuse the lines. And if you confuse the lines and you're off by sort of 0.2 or more, you'll lose marks. Guys, you notice that there isn't a plot there for transverse shear. Now obviously we've been assuming that bending moment is almost always going to be larger than transverse shear, so largely that will attribute the fact that you won't need one. If you do need one, you can make a best estimate as to which one of those would be most appropriate. Which one of those do you think you would use for transverse shear if you absolutely had to? Yeah, probably torsion. The other two are normal stresses, and the torsion is a shear stress. So in a pinch, you would have to very clearly explain the assumption that you need transverse shear because of this. There isn't a table for that, so you're going to use the torsional value, and if at some point someone decides that's not accurate enough, they can then go and find what the transverse shear stress concentration. So that's the point of having assumptions in an analysis. You have that assumption there such that someone can read it, and if they think it's bullshit, they know why it's bullshit, they can go and do it better than you. Alright, how are we going? Everyone had a crack? Alright, so the way I lay these things out is we just write down some ratios and the values. No need to stuff around. Alright, so what value of big D on little d do we get? 2. Little r on little d is 0.25, so therefore KT, what do we get? 1.54, anyone else? 1.54. 1.52, any other values? 1.525. So 1.52 I got. You know, anywhere around, I'd say probably with these factors, I'm pretty happy with plus or minus about 0.1. So anywhere between about 1.6 and 1.4, I guess. That's about as you know, far out with as you'd like to be. Try and be a little bit more accurate than that. We'll be good. Alright, second example. This one, page 167. Alright, so I have a flat plate in this circumstance with a notch in it on either side. Like so. Radius of 10 millimeters and a height here of 100 millimeters. And my loading has both the bending moments, like so, and an axial M and P. Find KT for both axial and bending. And so you might like to say sort of KT axial and KT bending, like that. Such that when you calculate your applied stresses, you can apply the right KT to the right stress to get your properly corrected applied stress element. We need a big one. Sorry? Well, that's the question, isn't it? In the absence of small h, what would you assume?
That the centre of the circle is along the top edge of the shape.
Exactly. So, in the absence of this information there, you'd assume that that point there along that edge is the centre of that circle, the centre of that circle. So you take 2r off 100 and you get your small h. Now that's not necessarily the case because that notch can be recessed down, but in that circumstance, unless I've stuffed it up, I'll tell you what the small h is. Or you can calculate it yourself or measure it or whatever. Alright, has everyone got a value? Values. What's my h? So capital H on lowercase h ratio. Say again.
5.4, 1.25.
There you
What's your unit?
go. Okay, and my radius on my small h. 0.125. Making KT axial equal to, what do we get? 2.3. Anyone else got anything different to that? Yep, 2.3. 2.3. So those type of notches, you're decreasing down to 80 mils from 100 mils. It's over double the stress right on that edge, which is pretty significant. What about in bending? 1.9. Yeah, that's better. 1.9. It's a little bit less critical in bending. So if we think about it, the bending's already maximum at top and bottom there. So already the stress lines or the force lines are congregated there as it is. So that, theoretically the concentration has a little bit less of an effect there because they're already there. Does that make sense? But yeah, those two values apply then to the different stresses.
What does the infinite line mean?
The infinite line.
Yeah, so when h is like small h.
That basically gives you the ability to interpolate. Alright. So if h on h is 2, say, you know it's not up here. you know that H1H basically converges to an asymptote there. So 2 will probably only be a tiny little bit above that. 100, you're probably verging towards that infinite line. Yeah? So that gives you a bound for, you know, these curves will not solve every single problem you ever have. You need to be able to sensibly choose a value perhaps outside of what you know. And again, make an assumption, write it down, make sure it's recorded. But you know, everything between 1.5 and infinity is between that little line, so you're not going to make too much of a stuff up just choosing something in the middle. Make sense? Cool. All right, let's do a proper example. Alright, so we have some sort of bar here. And it's got some sort of distributed axial load on the each end of E equals 45 kilonewtons. I've got this dimension here as 25 millimeters. This dimension here as 15 millimeters. Now, obviously that one's 15 as well. This dimension as 100 millimeters. And this dimension, which is the diameter, 50 millimeters. Alright, so I want you to tell me the maximum value of stress at the hole and the maximum value of stress at the semicircular notch, and I'd like you to indicate where on the hole and where on the notch that stress actually occurs. And let's put assumptions down. Now, an important assumption that I'm going to add to your list of generic assumptions that you use every single time is the material is homogeneous and elastic. Alright, so it's elastic in so much as things start going very weird once it's in the plastic zone, so we don't want to analyse for that. We want to make sure we don't get to that in our design. And homogeneous just means it's the same material properties everywhere and it's consistent, so it doesn't have little things like bubbles and voids and problematic bits like that. It's been manufactured well. Now, if I had tiny little bubbles in this, what would happen at the tips of the tiny little bubbles? Stress concentration. And so if we have tiny little bubbles throughout the cross-section of something and we've got massive stress concentrations, remembering that a tiny little bubble is about as bad as a little crack, we've got bad stress concentration, and so bad material equals failure very, very quickly. If you do welds and it's on something critical, a lot of the time they will do x-rays of those welds to make sure there is no bubbles and crap in the welds, because they're getting a lot of loading and any sort of bubble will cause a fault. And so if you're doing things like really critical pressure vessels and aeroplane wings and that kind of stuff, any welds that are done on those things get x-rayed, every single one of them, to make sure the weld is done right. for exactly this reason. And for fatigue, but fatigue comes from stress concentration, and we'll talk about that. All right, so give that a go.
How far? If they were really close together, I feel like would that make a difference?
It does. Yeah. So, guys, we'll talk. We'll use an Australian standard called AS 1403 for rotating steel shafts, and in that standard, they actually deal very well with combined stress concentrations. They have an equation in there or a set of rules in there. If stress concentrations are within this distance of one another, you need to use this concentration factor plus 0.5 of that concentration factor or whatever. So if those concentrations are close together, they start having a combined effect. If they're far enough apart, then they don't. So you could add an assumption there if you wanted, assume concentrations far enough apart not to affect one another. That would be a very good assumption right there. Alright, in the interest of time, does everyone have a bit of a go at that? Everyone start and get a little bit more comfortable? Or at least stretching your brain enough to retain some of this stuff? So, analysis. Alright, so our assumption here is that they're separate, which means that we can analyse them completely separately. So I will analyse the whole first. First thing we do, you can either calculate the stress concentration factor or your normal stress, it doesn't matter. Those are the two things you need to know. So let's say nominal stress. Now nominal stress, it's a normal stress based on axial type loading. Nominal is P on A. P we know as 4,500, and what is our area? So if I'm looking at this hole, take a cross section. So it's going to be 100 minus 50, so 50 is this, or 25 and 25 times the depth is 25. It's whatever area is left. So the force is being carried over the area, which is sort of contributed by this part and this part. Right, so that's the area that carries the force. So that's the area we use for our nominal stress, which is 100. Or if we're going to do what we should do is write in meters. 0.1 minus 0.05, and that's times 0.025. So what do you guys get for nominal stress? There? What's that in? That's the area you know for normal stress, the actual value of normal stress. 36 megapascals. 36 megapascals, or 36 by 10 to the 6 pascals, whichever. Alright, now we need our ratio for KT cal, and that's little d on b equals 50 on 100 equals 0.5. Do we need anything else for our calculation? No, that's everything? We need R or something else? Oh, yeah, right. Oh, good. So that basically gives us our line. What value do we get? When we do this, I would say from figure 4.40b KT equals something. That way, if someone comes and reads it and you haven't used the table out of this thing, it's basically referencing. So if you use a table online or out of a different textbook or something like that, you say where you found it, because not everyone will be working out the same textbook for this stuff. You could just, for this subject, basically say this. If you actually write up a report and you're doing this sort of stuff, you might actually reference which textbook you use, so you have like a reference there. What we get for KT? Anyone else?
2.5.
2.5. Yeah. Anyone else? 2.5? Yeah, so somewhere in that 2.25, 2.5 range. Most of you got 2.5, did you? Yeah, cool. Let's use that then. Therefore, maximum stress at hole, sigma max, and I'll just put a bracket hole, equals KT sigma nom equals 2.5 times 36, because I'm just working megapascals, equals, what do you get? How much? 90 even? Yep. 90 megapascals. Alright, and then what I did was just draw this, and you can sort of draw your stress profile looking like that. This is hard to me just so you guys know what it looks like. And so your maximums either at the top or the bottom there. This value here is going to be 90 megapascals, and this value here is going to be whatever our normal was, 36 megapascals. So you can see the hole makes a significant difference here. Alright, so the last one is our notch. Same layout, so nominal stress. Sigma nom equals P on A. P doesn't change, so 45,000. And A in this case is going to be the cross section minus the 2 notches, so that's 0.1 minus 0.03 times the depth, which is 0.025. And what everyone get for that? Not the, just the stress, yeah. 25.7 MPa, great. And then we can have our ratios for KT calc. And so that's H on H equals 100 on 70. No, I'm using millimeters here because it's a ratio, so I can. It's not just because I've made a mistake. 1.43, and the other ratio is little r on little h. 15 on 70, 0.21. Alright, so therefore from figure 4.39b, KT equals, what we get? 2? 1.95, anything else? 1.95? Yeah, somewhere around it. Let's use 1.95, that's fine. Therefore, maximum stress at notch, sigma max, and we'll put a little bracket notch, equals KT sigma nom, equals what we get, 1.95 times 25.7 equals, what's the result? 50.1 MPa. So we'll underline, and just to stick with convention, I'll draw this so we're fully confident of what that looks like. In this circumstance, looks like that. And we get this there and there being our critical zones. This value is 50.1 megapascals. And this value here is whatever that was, 25.7 megapascals. Alright, let's do a sanity check. Does it make sense if this is 90 and that one's 50? Why?
There's less. One's got 70
Mils in height.
One's got 50.
Other one's got 50. Yeah, easy. Yeah. Every single solution you give me, look at the answer, and if you've got literally anything to compare to, ask yourself, does it make sense? Because that'll help you not only to get it right in the exam, I'm much more interested in you guys being good engineers. And good engineers question absolutely everything they get because you know and you're confident that a certain percentage of the time you're going to get it wrong. And you need to be able to catch that every single time. Cool. Alright, that's everything I've got for you guys. I'll see you guys Monday morning.